Okay, hello everybody. My name is Duncan Coutts, and I am the technical architect for Cardano, and in particular for the new implementation. So my talk today is supposed to be about the architecture of Cardano, and the way I'm going to try and approach it is to look at more the questions of why. So yes, I will cover what is Cardano, what does it consist of. I'll look at a bit at the what questions, but primarily I want to focus on why are things the way they are. Why have we made these design choices? What motivated them? Which ones are forced and which ones are accidental or just standard practice. So yeah, I'll hopefully try to give a good impression of why we have done things and the design principles that come from the design constraints, and then some of the choices that we have made. And I'll take Q&A perhaps as we go through, if certain questions come up that are relevant as we go along, and otherwise I'll try and focus on questions at the end. Okay, so let's start with the what. So I'll start at the top level, like what do we have, what components do we have, and then we'll dive in, and then get to the why questions. So let's just start with the major components of the system. We have the node, right? The node process, an operating system process. That is, a central chunk, a central piece of the system. So the diagram here is meant to indicate on the left that it communicates to lots of other node processes elsewhere, in the network, elsewhere on the internet. And we use a node-to-node inter-process communication protocol for nodes to talk to each other. And then on the local side, all these other processes, these are meant to indicate processes that run on the local machine. So if you like, there should be a great big box drawn around all the ones on the left-hand side, which are, these are all components that run locally, whereas the ones on the left were other processes running elsewhere on other hosts elsewhere on the internet. So we have this node-to-client IPC protocol, and this is how the other components talk to the node. So we've got the command line interface, we have a command line tool for interacting with the node, submitting transactions, building transactions, querying the node. We have the wallet backend, and it talks directly to the node using its local node-to-client inter-process communication protocol. And that's what, of course, you have if you're using Daedalus. So a standard Daedalus deployment is a node process and the wallet backend, and then also the Daedalus front end. So that's the standard deployment there. But a deployment at an exchange, for example, would not use the wallet backend, perhaps, if it was a large-scale exchange and they were integrating in a more deep fashion. They didn't want to just reuse our wallet backend. They would use some of these other components. So in particular, one of the very important components in the architecture here is this DB sync component. And what that does is it reflects the blockchain data into a database. And these are two quite different presentations of the same data, and they're both extremely useful for their different purposes. So the DB sync is this converter that continuously live synchronizes the blockchain data into an SQL database, and then from there, there's lots of other things that you can do with that data once it's in a database format. You can no longer interact with it as a blockchain, but you can ask state questions. Give me all the things such that, filter conditions, joins, all the great stuff that you can do with standard SQL databases. And so there's a few other components that are built on top of that Postgres database using the data from the database. So we have a GraphQL API server. We have a REST API server. The GraphQL one is the preferred new one, but we have the REST one as well. And then there's another one, there's the Smash server. This is a metadata aggregation server. This is the one that we use to allow the Daedalus to find out all of the pool's off-chain metadata. So when pools register, they register like their ticker name and their homepage and whatever. That metadata gets hosted off-chain, and the Smash server is an aggregation server to collect that metadata from all the different pools and provide a nice, easy-to-use aggregation for the wallet backend and Daedalus to make use of. And that also gives an opportunity for a bit of pruning. So Daedalus can. So it means that the Cardano Foundation, for example, could have a list that says we're going to exclude these ones that use profanities, or someone else could have their own. It sort of squares that circle of how do you do a bit of curation and also provide it, still have a properly decentralized system, and that's the solution there. So the point is there's a bunch of different components. Some components talk directly to the node using this relatively low-level node-to-client protocol, and then many other components. The appropriate data source is the Postgres database, and those are two different views of the same data. And which one is appropriate depends on what the component is doing, and we get both. So let's focus in. This is now looking in on what's inside the node, and this is one of those sort of classic block diagrams that abstracts over lots of details. So just as a big picture here. So at the very top, we've got this sort of relatively thin layer that is the node top level, because all of the interesting bits live in other components, other libraries lower down. The two really large chunks of functionality is the consensus chunk there, and then the libraries for the ledger rules. But let's just go from the top to bottom, shall we? So the top level, we've got the node, and that's really top level integration. It's got the command line, it's got configuration files and how to start the thing up. It makes use of it. It ties in with the logging and monitoring subsystem. So there's a whole separate library for dealing with monitoring and logging, and the node top level pulls all those things together. Then going down one level into the consensus and ledger area, this is really the guts of the system. So we have consensus and we have ledger components, and those actually don't depend on each other, which is perhaps surprising at first. We'll get later on to why that's really a very helpful thing. But because they don't depend on each other, we do need something to ultimately pull them together. So we have, again, a relatively thin layer that says, okay, we're going to take this particular configuration of how the consensus is used, with this particular choice of protocol, and we're going to combine it with these set of ledger rules, like the Byron ledger rules, or the Shelley ledger rules, or the composition of the two, one after the other. Because of course, as we all know, for the real Cardano network, we have to do this hard fork from Byron into Shelley. So the ultimate protocol that we are going to be running is the composite protocol of both ledger rules sequentially, one after the other. So that's what that integration layer does. It selects the combination and glues those bits together. So then diving down one layer further and looking at the consensus side, this is a substantial chunk of functionality. This is the implementation of the blockchain itself, right? Not the ledger rules, not the rules of what happens of the data that lives on the blockchain, but the implementation of the blockchain itself. So in particular, that's the implementation. That's where Ouroboros lives. Right? Ouroboros is our blockchain algorithm. That's our consensus algorithm. Various members of the Ouroboros family, and that's where that lives. And it has various major pieces of functionality within it, such as the chain database, the storage of all the chain data, the mempool where transactions live transiently, and it has this support for doing hard forks, which I'll come back to a little bit later. And I also want to advertise, if you're particularly interested in that bit, my colleague Edsco has a talk specifically on the hard fork compilator, so I won't go into too much detail about that one. Then over on the other side, we've got the ledger rules. And again, these are written relatively in self-isolation, which is good for being able to understand them, being able to test them. And they, particularly the Byron and the ledger ones, they are separate from each other, because they're quite substantially different sets of rules. We really redesigned the Shelley ledger rules completely from scratch. So the best way to do that was to have them be separate, isolated chunks of functionality that we can then compose at the higher level. Obviously, below that we have all of our cryptography libraries. The ledger, of course, depends on cryptography for validating transactions. And then the lowest one at the bottom, underneath consensus, it's not really a hard and fast line between where does consensus end and network starts, but we've tried to draw a line that makes sense between them. So this is networking, not completely generically, it's networking to support consensus. And there's a whole lot of interesting functionality within that network layer. Because of course, the node is a networked component and it interfaces with adversarial peers, in a networked environment. So the networking is a substantial chunk of functionality and is quite interesting and tricky. So those are the major areas within the node. So that's the what. So let's look at starting. Why are things the way they are? So to do that, we really have to start from what are the requirements? Why? What problem were we trying to solve? So many of the design principles and then design choices really come from this specific challenge that we have, which is that we have to implement the Ouroboros algorithm faithfully. That is, implement the paper correctly. And we have to do that while meeting real-time timing constraints. Right? This is a hard real-time system. The times are measured in seconds and not milliseconds, but it's nevertheless a hard real-time system. And we have to do this in an environment where anyone, you have to sort of assume everyone, is out to get you. You have to think in a paranoid way when implementing this kind of system. Because if you don't, that is the way that someone will exploit it. And there is every reason to do so because there's money at stake. So, they really are out to get you. It's not just your paranoia. That's the way you have to think as a designer of a system like this. And this is really hard, right? This is really very difficult to do, even in theory. There's some, if you were try to really prove that you could do this, it's a very difficult challenge to demonstrate that this is technically feasible, even in principle. So let's jump into what makes this a hard problem. And I think it's useful to start by comparing proof of work and proof of stake. And obviously, Cardano is a proof of stake, Ouroboros is a proof of stake algorithm. But why is this any harder than proof of work? Aren't these things, sort of theoretically equivalent in some way? Well, here's the key thing. It's all about the balance of resource costs between the attacker and the defender. Okay, so what do I mean by an attacker and defender? So think of yourself as being the node, right? You are the good guy, you're the defender. And there are adversaries out there on the network that are trying to interact with you in such a way that they can gain some kind of advantage. Perhaps they can make you become overloaded, or they can get you to accept bad data, or they can simply block your interactions with other people in such a way that they gain some advantage. Taking your node down just while it's your turn to produce a block, for example, or somehow managing to systematically overload the whole network and make the whole thing fall over. Those are the kinds of things you have to be thinking about, and not by specifically trying to avoid each specific one, but you have to sort of think more systematically and say, how do I design something that, with positive evidence, that we positive arguments that we believe it to be robust. So it's not about whack-a-mole of trying to avoid a catalog of known problems. It's about trying to thinking about a positive argument as to why your system should resist any interaction with an adversarial player. So in proof of work, the defender has a massive advantage, which is to do with the proof of work itself, which is that the proof of work that lives, which is literally this little piece of data that lives in the block header, is extremely expensive to create, but it's very cheap to verify. And that balance of resource costs is then firmly tilted in the favor of the defender. It's extremely expensive for the attacker to make one of these things, and very cheap for the defender to check it. And from that stems, the ability to make a fairly easy modular design. What do I mean? You could adapt an ordinary off-the-shelf broadcast algorithm and use that for broadcasting blocks across the network. And you would just need to modify it slightly with a little filter condition that says, check the proof of work. And you can check that proof of work with no context whatsoever. And that on its own is enough to, you don't even have to check that this block chains onto a previous block, because just checking that the proof of work is correct already means that you're limiting the number of blocks that can be sent to you that you would have to consider. It's now limited by the total hashing power in the whole world, and that is that's already imposing a limit, which is a lot easier to deal with. Whereas on the proof of stake side, we don't get anything like that. The cost of verifying the signature versus the cost of producing the signature is about the same. So it's very finely balanced in terms of the resource costs between the attacker and the defender. And furthermore, we require a whole lot of context to be able to verify the signatures in a block header. We require the full ledger state, or at least a very, very recent ledger state. So it doesn't, we can't get away with just like with the proof of work. You just look at the proof of work on its own, no context, and check that it's okay. With the proof of stake, knowing who's supposed to sign that block, you can't just check the signature. You have to know who is supposed to be signing that block. That itself requires having a ledger state for the whole previous rest of the chain up until the very recent past. And so this means that you can't have this very simple, easy modular design. You have to have interaction or interleaving between the network and consensus concerns. So this means that the implementation is more complicated, and we have to pay much more close attention to these issues of resource costs. So that's the key problem, this balance of costs between attacker and defender. And that really motivates a lot of the design principles and design decisions that we have taken. So in particular, we have to design for worst case asymptotic complexity in adversarial conditions. That means we have to think about what interactions are we setting ourselves up for? Because we define the protocols of interaction, like we're using TCP, where we design these application level protocols. So we have to think about what, given those protocols, given those interactions that we are allowing ourselves to have with the adversary, what is the worst thing that they can do? And we have to think about that. There's a technical term to this as well. Worst case complexity is a technical meaning, which is as opposed to, say, amortised complexity. And the technical reason there is that it's the adversary that gets to choose what they do next. So it becomes hard to you can't kind of average things out across many interactions very necessarily. I mean, there are techniques to make that possible, but in general, you have to think about what's the worst thing they could do at every single step of the way. Because what goes wrong if you don't think in those terms, then suddenly the attacker can do something that's very cheap for them that causes you to incur a great deal of cost. And if they can do that repeatedly, and you don't take care of your resource costs in this way, you can be overwhelmed. Your node can be overwhelmed by doing work that's caused by an attacker, and that can stop you from doing useful work. And that becomes a denial of service on the node. And that's just the kind of thing we need to avoid, because that allows an attacker to leverage a small amount of resources to execute an attack, let's say on all the relays in the system. It might not be very expensive to make a TCP connection to every relay, and if you craft some particular form of interaction that causes all the relays to go away and think for 10 minutes, then you've taken down the system for 10 minutes, or perhaps you can keep it down persistently. We have to only rely on trusted or local information. Trusted information from the blockchain after we verified it, or things that we can locally observe. We cannot share information between nodes without it really kind of at all, unless it's stuff that's like on the blockchain and is verified. So we can't share like reputation information very easily, because we can't trust our peers. Another design principle is that we have to minimize the difference in resources, but memory use particularly, between typical and worst cases. And this is quite counterintuitive. What do I mean by that? We have to make sure that, basically we've got to make sure that we use a constant amount of memory, and that we don't optimize for the good cases, and then when bad things start happening, suddenly we take 5 times more memory. That would be really bad if that were the case. Because that would mean that when the adversary can push us into a more complicated situation, they can cause us perhaps to exhaust our memory requirements. And you might say, well, why don't you just allocate 5 times more memory than you need? Well, the thing is that we don't control all these nodes, right? These nodes are all being operated by other people, by IT operators, and if people will scale the size of the amount of resources they dedicate to a node to what they see it typically using. So if you see that your node, you're running a Stateful, you're running a relay, and you see that the node is typically taking, let's say a couple of gigabytes, you might provision, 4 gigabytes, let's say, or 8 gigabytes or something on your cloud system or your bare metal system or whatever. And now suddenly, if in adversarial conditions, when an adversary is really trying to mount an attack on the system, if you've designed the code in such a way that suddenly you take 5 times more memory in those sorts of scenarios, then the system's going to run out of memory. So it's actually the counterintuitive thing is that you should not optimize to save memory in the optimistic cases. You should only be looking to save memory that you can be sure you can do in all cases. So that's the thing about minimizing the difference in memory use between the typical case and the worst case. Because if the adversary can cause the worst case, then they can push you into resource exhaustion in those worst cases. So it means that sometimes you have to leave kind of optimization opportunities on the table, because it would only be an optimization opportunity in the average case and not the worst case. And another design principle that's extremely important is we have to have graceful degradation under excess load, or even better, remaining at peak throughput even when the load that is presented is higher than we can handle. And again, if you don't do that well, that's another method by which someone can execute a denial of service attack on you. So there's also some design decisions that come with this. We have to, with Ouroboros, we must interleave our validation with chain relaying. So that means that we're interleaving aspects of the networking and consensus. We can't have such a clean separation as you might be able to have under proof of work. It also means we've made a decision that we use stateful protocols. So we're not using stateless HTTP. We are using stateful protocols, and we are using always consumer-based control flow. This links back to the principle of we want to make sure that we remain at peak performance and don't get overloaded, even if more work is presented to us. And consumer-based control flow is one of the techniques that we use to achieve that. And then a very an aspect of the design that comes from this that turns out to be a major sort of organizing principle of the whole node is this stateful chain following protocol. And I'll talk in a little bit more detail about that one. So okay, what is the? Let's go through each of these major three major examples of design decisions that we made and where they come from. So as I said, the validation, we have to interleave validation with relaying blocks. Otherwise, we're just forwarding nonsense around the network, and we're using up our own network resources, perhaps to the point of exhaustion, with useless nonsense that an attacker is causing us to send around. So it's really important that to prevent that, to make sure that we don't exhaust our own resources, that we only forward information that is valid. And we also know that we need the full ledger state for header validation. That's necessary for validating the signatures. So that means that just to look at the headers and validate those headers, we need this full ledger state. So you can see we kind of have to interleave kind of recursively between things are happening on the consensus layer and things happening at the network layer. We validate headers and blocks on every single hop. I mean, this may seem paranoid, but frankly, I can't see how to do better. And perhaps there are some ways, but we're starting off at least with this very conservative way of let's validate everything, because the argument of are we making sure that we're working within our resource bounds and that we're not opening ourselves up to these denial of service attacks is much, much clearer to see when we're validating everything on every hop. So this prevents bad data and wasting resources, this approach. And we will immediately disconnect from bad peers, because by validating on every hop, it means that if someone sends something to us that's bad, we can pin the blame on them, right? Whereas if we followed an approach where it said, you don't validate on every hop, you validate on some hops, then if someone sends me bad data, do I know that it's them that was trying to fool me, or was it someone who was trying to fool them? Now I can no longer tell. Whereas if we say no, everyone must validate on every hop, and then if I see that you send me something bad, I can immediately pin the blame on you and disconnect from you and move on, so that you can't do anything further. Another design decision, I said that we use stateful protocols and consumer-based control flow. So what does this mean? So this means that we use long-running sessions like TCP sessions, and rather than say HTTP, where logically speaking, at least, each request is separate and there's no state that's held between them. Whereas we allow ourselves to make use of state on both sides, the client side and the server side. I mean, in some sense, all protocols are stateful. It's just a question of which side is the state on. Is it on just the client side, or is it on both? And what people typically mean when they say stateful protocols is both. I mean, HTTP is stateful in the sense that there's client-side state and there's no server-side state. That's when they say it's stateless. That's what they're really referring to. So yes, we will allow ourselves, the extra tool of having server-side state as well. And it turns out that we really make effective use of that. And the other theoretical advantage that those stateful protocols give us is the ability to do some amortized complexity, to make some amortized complexity arguments as to why we're not opening ourselves up to denial of service attacks. Because you have a sequence of interactions over a long-running stateful protocol rather than a sequence of isolated interactions, it means you can tie those together, and you can say, we'll only do this expensive operation after we've done some other number of cheap operations, or perhaps we do something like saying, we'll do an expensive operation, but we'll insert a big delay. And you couldn't get away with that, inserting a big delay, if this were an operation that you did it in a stateless manner, because you'd have no context in which to do it. So simply the fact that we can link together in a single session many interactions means that we can start to look at the costs across the whole series of interactions, rather than having to look at worst case complexity of each interaction on its own. And as I said briefly before, the pull style protocols really allow us to avoid being overloaded. This is such an important design decision that we've got here. So imagine it like this. Even for transaction submission, right? You don't push a transaction in this system. The way that transaction submission works is that you sort of would like to say, I am sending you this transaction, but that's actually not the way it works. The way it works is, at the beginning of the interaction, we say, I am prepared to receive one new transaction from you, or I'm prepared to receive 10 new transactions from you. Please send me 10 transactions. And then the other side can then send 10 transactions. But that's only because they were asked, right? And if the consuming side is overloaded, it simply won't ask you to send more transactions until it's ready for them. And you can't preemptively send the transaction without being asked, because that's immediately a protocol violation, and the connection will be dropped. So this means that we can always do all of our interactions in this pull style. So we only ask for more work to do when we have the capability to do more work. That's the key idea. And then in particular, we have the stateful chain following protocol. Now, why do we have this? We are making use of this server-side state business. It turns out that following a constantly forking chain in a reliable and simple way is a bit tricky, especially if you try to do it in a stateless style of interaction. If you were to try to write down, in a big, control flow graph or chart of what are all the possible interactions that you would have to do, if you write that down, that ends up being quite complicated, because there's all these sort of corner cases of, what if the chain has changed since the last time I asked? Whereas if you allow yourself as a designer to give the server side just a little bit of state, it turns out that you can design a protocol where everything becomes quite simple again. And the trick is, as it turns out, that you make the server side remember in the sequence of interactions of this protocol, you make the server side remember what point on the chain is the client at. And just remembering that one thing is enough to return us to a nice, simple protocol. Why was this complicated in the first place? It's because of the fact that it's forking. Right? If you were just following a sequence of events, and the sequence of events were always final, everything would be fairly straightforward. But it's the fact that the things can fork that means that when you ask for the next header, well, maybe the chain changed in between. Whereas if the server side knows that the chain changed in between, and it knows what point you were asking for last, it can say, I know what you need to do. You need to roll back to here, and then carry on forward. Whereas in a stateless style, you have to re-establish where does my chain and your chain intersect before we can figure out which block to move on to. So this gives us a nice, simple, easy to use protocol, but it does rely on state, server-side state in the protocol. And we use this chain following protocol both for headers in the node-to-node case, and we use it for whole blocks in the node-to-client case. So the interesting thing here is that the motivation for this thing was security, protecting ourselves against denial of service attacks, and performance. But actually, it ends up leading to an organizing theme for the whole architecture, and I'll talk about that more later on. So we have the node is really characterized by interaction via protocols. And protocols are a big deal in this. We have protocols between nodes, and we have protocols between nodes and clients. And that gives us a lot of reuse, actually. We can reuse a lot of infrastructure that we built. You need to have protocols for nodes to talk to each other, and we're able to reuse a lot of that machinery for interactions with local clients through protocols that we execute locally. So what have we got here? We've got two categories of protocols, of application level protocols. Right? So we have chain synchronization, and we use that both for the node-to-node case and the node-to-client case. But as I said before, the difference is that in the node-to-node case, we execute chain synchronization just with block headers, which are fixed size, and that limits the costs by doing it with fixed size headers. And then in the node-to-node case, ultimately you have to download block bodies, but you don't want to download block bodies from everybody, right? That would be extremely wasteful. So we want to, do chain synchronization with our peers and figure out what chains are available, but then only fetch the block bodies from one or maybe two of them. So we have a separate protocol, application level protocol for fetching blocks. And then finally, of course, we also have a protocol for submitting transactions. And that's it, right? That is the sum total of all the interactions between nodes, which is really a very narrow interface. And if you compare this, say, with, well, actually, really with many other node implementations, you can go and read their reference on their network protocols. They're quite big and hairy, and have lots and lots of RPCs and whatnot. I claim that this is really quite simple, and we've got nice diagrams, well, looking like this. I'll come back to that one in a sec. Lots of these diagrams that just fit on a single page that show you this is the interaction of this protocol, and so each one is quite simple. So there's another design principle here, which is that we are using many small, simple application level protocols. So we don't have one big protocol that deals with all aspects of sending headers and blocks and transactions. We have three separate, so we have a degree of modularity here, three separate application level protocols, but we run all of those protocols over a single TCP connection in the node-to-node case, or in the node-to-client case over a local socket. So let's look at also what we have on the node-to-client side. So we've got chain synchronization again, same protocol, but this time instantiated with whole blocks rather than with just headers. And that's because in the local case, we don't need to worry about denial of service attacks. So we use chain sync there. We also have transaction submission, of course. It's a slightly different transaction submission protocol in the node-to-client case than the node-to-node case. In particular, we return error messages in the node-to-client case, whereas you actually don't want to reveal information in the node-to-node case. And also in the node-to-node case, we have to care more about performance and latency, whereas in the local case, we don't have to care about latency. And there's one genuinely additional protocol in the node-to-client case, which we certainly can't reveal in the node-to-node case, which is a protocol for querying the state of the ledger state of the local node. That is an expensive thing to do, to reveal that. So it's okay to do that for local clients because, as we said, you don't have to worry about you DDoSing yourself. That's not a thing we have to worry about. Whereas we would have to worry about that in the node-to-node case, and so we don't reveal that information in the node-to-node case. But so that gives us access to the current and actually in fact recent ledger state for the local chain, and that's what a lot of the local clients use, is they're executing queries against that ledger state. Now I included this slide really just to show kind of how simple it is. I'm not going to go into details about this, but the kind of point is that this is a state transition diagram for our main protocol. And the fact is it fits on one slide, and there's only 4 states, and there's only, 1, 2, 3, 4, 5, 6, 7 messages, right? This is really a remarkably simple protocol for the power that it gives you. And we've tried to design all of our protocols in this way, that we think about them carefully to make them as simple as possible. Simplicity is hard to achieve, but I think that is what we've done here. Right, I'm going to try and give a quick overview then in the more technical details of how is the node internally organized. So I'm going to try and explain this diagram a bit. So bang in the middle, we've got the chain database. Right, this holds the current chain state, which includes both the chain itself and also the ledger state. That is all the information that the ledger needs to be able to validate new headers and new blocks. Now the little blue circles all over the place, these are meant to indicate other threads, and the ones where we've got groups of 3 of them, that's to indicate that we are having threads, one per other client, other peer that we're interacting with over the network. So we use concurrency and threading for modularity here. So you have a a protocol thread that talks to another peer, and for our application, we have a protocol thread per protocol that we are running. So for example, we've got chain sync protocol and the block fetch protocol and the transaction submission protocol, and we've got the client side and the server side of each of those, which is a lot of threads. But that's okay. Haskell's lightweight threading makes that a perfectly reasonable thing to do and lets us preserve this nice modularity. So that's what we have. We have threads that deal with the protocol interactions for each of those things. And then how do we make use of them here? So starting from the chain sync protocol client side on the left-hand side of the diagram, this is the one that follows the chain of each of our upstream peers. So each node will have a small number, like a relay might have 20, and a deadless user might have 1 or 2 upstream peers. And we're looking at the chains of those peers, not the whole chain, not with the blocks, just the headers. And we validate those headers. The chain sync client asks for the next header, and it validates those headers. If it finds any invalid ones, it'll immediately disconnect. And so then that means locally we have a copy that's continuously synchronized copy of the headers of the last k blocks, like a couple thousand, of each of our upstream peers. So we can see their headers and we can look at them and say, which chain would I like? Are any of those chains longer than mine? Should we be downloading any of the blocks corresponding to those chains? And that's what the next component is, the block download logic. It looks at all those sets of upstream peers headers that we know are already valid at this point. Any invalid ones would immediately be deleted and disconnected. We look at all those and say, yeah, are any of them longer? If so, which is the longest one? Which one do I prefer? The question of which one is preferred is a question that the consensus algorithm answers, and the block download logic simply makes use of whatever the policy is. But of course, the way it works with Ouroboros is that it's longest chain and a few other details. So then we decide which blocks we're going to download and from which peers. And there's relatively complicated logic in there as to to do with timing and networking as to which peers we actually end up choosing when because there are often many choices. So we'll try to choose the one that's best, quickest, fastest. And then that gives us that we then instruct the threads that are running the block fetch protocol to go and actually use the application level protocols, go and ask the other peers for, give me that block. And as and when those blocks are fetched and downloaded, they are presented to the chain database. And that's the chain database that really makes all the final decisions. So it sees all of these blocks have been downloaded, and it looks at them and says, okay, let's run the Ouroboros chain selection algorithm on those and decide which ones, if any, to adopt. And that's where we do the full block validation, running all of the ledger rules on all the transactions within those blocks, and picking which blocks are we going to adopt into our own chain. And then that's what it does. It adopts, if they're valid and according to the Ouroboros chain selection rules, it picks those blocks and adds it to its current chain state. Then the blue circles on the right hand side, those are now the same protocols, but the other side of them, the server side of those protocols. So here we are serving downstream peers, and we're giving them chain sync protocol, we're giving them headers, and we're also interacting in the block fetch protocol to be able to serve up blocks to our downstream peers. Up at the top, we have all the things to do with transaction submission, both the client side and the server side of that protocol. And in the middle, we have the mempools. The mempool is where transactions that are coming from our upstream peers, well, I suppose technically they're downstream peers, but the client side of the protocol, we receive transactions from them and we validate them and put them into the mempool. And then similarly, we serve up the contents of our own mempool via the transaction submission protocol, but now the server side of that protocol. And then the relation between the mempool and the chain database is we have the mempool is continuously, on appropriate changes, is revalidated when the chain database changes. So we will delete from the mempool transactions that have now made it into the chain database. And then in the other direction, information flows from the mempool to the chain database by block forging. So if we're running a node that produces blocks, then that's what happens with the block forging. When it turns out to be our turn, we take the current contents of the mempool and pack as many transactions as we can into a block and present that to the chain database. And then everything else follows through out the other side using chain sync and block fetch. So that's the kind of key internal architecture of the consensus and network, how they all interact with each other. So this leads us to this kind of interesting style of architecture, which is actually an existing, relatively well-known style, which is called in industry event sourcing. And people choose this style for different reasons. We come to it here because we're kind of forced into it by the way, by all these design decisions and the need to, this chain following protocol leads us to this event sourcing style. So what is it? What is this style of application? This style of information data management? So I'll do it by contrasting it with another standard style, which is basically kind of database style. So that's state query. So in event sourcing, what we do is we maintain a log of all the changes, which of course is the blockchain. Right? The blockchain is that record, that log of all the changes to the state of the system. And applications interact with event sourcing architecture by processing the sequence of changes, perhaps from the beginning, or perhaps they disconnected and reconnect and they jump to halfway and then they carry on processing the log of changes from that point. And so applications that are in this style often make use of message queues, things like Kafka and other. So some message queue systems are kind of ephemeral, and others are more persistent, where you do have a persistent log of all the transactions or changes from the beginning. Whereas the sort of more traditional style of IT application, data processing application, is this sort of state query database style, where there is one current state typically maintained in a database of some sort, and that state simply changes as the world changes, as it interacts with the world. So that's the key contrast, right? In the state query style, you have one state, one current state that changes live as things happen, and you can only really generally ask questions about the current state. Whereas the event sourcing style says it doesn't actually anywhere maintain the current state. It simply maintains the log of all the things that have ever happened, and applications maintain the bits that are interesting to them about a current state. And they may maintain other indexes or additional information, but the ultimate source of data is just the list of all the changes. And so that fits the blockchain style extremely well. But there are many applications that would like to work in that state query style. In the state query style, the interaction is, if it fits your application, it's quite simple. The application simply queries the current state. And the obvious examples of that are SQL databases, REST APIs, GraphQL APIs. You simply ask the question, gives you the answer based on the current state of the world. So both styles are useful. The event sourcing style is kind of pretty natural for blockchain itself, but many applications would like to see the world as if it were in a state query style. And the way to deal with that is to turn one into the other. So in some sense, the event sourcing style is fundamentally more flexible because you can go from event sourcing to state query, but not really the other way around. And that's what we do with our DB sync client. And we reflect the state of the world into an SQL database. Now let's see, I'm taking a little longer than I was expecting, so I may decide to cut some of my later slides and go to questions. Let me just see what we've got coming up. Yeah, I think I will take questions now, and then if we have time after immediate questions, I have a bunch of sort of extra slides where we can look at some of the areas. So I will skip Kevin's question for a second that he's kindly fed to me. Okay, Kabir asks, can you explain a little more about how this affects the requirements for relays and separate block producing nodes? Will these nodes need to be on separate machines? The answer is yes. Relays and block producing nodes really ought to be on separate machines, but that's really primarily for the purpose of security. Your relays are public-facing nodes, and you don't want to have your private block signing keys being on those nodes. I mean, we do operate, a hot-cold key mechanism. So, if your hotkey does get compromised, it's not the end of the world. You can replace it, but you'd rather not. So, for that reason alone, I mean, it makes a lot of sense to protect your block-producing node with relays. It's also important for the system as a whole to have enough relays to support all of the users of the system, and it's also important to have these relays so that you become the system is a harder DDoS attack, right? If you want to, DDoS, DDoS is a very primitive but quite effective method of attacking a system, and you can resist DDoS attacks much more easily if you're a bigger, wider, fatter target. So by not making your block-producing node be exposed on the internet and only exposing one or several, well, it has to be several, not just one, otherwise you haven't increased the size at all, but exposing several relays, combined with the fact that Preos means that you don't know who's going to be producing the next block, it means that now you present a much bigger target for a DDoS attack. You really have to take down kind of a significant majority of the public relays to be able to DDoS the whole system. John Titus asks, do you guys just sit around and talk all day? I mean, I don't know to what extent you're joking, but I'll take that as a serious question. And the answer is, to a large extent, yes. That's actually a remarkably important aspect of designing these things. If you jump in straight away and crack out some code, you do a lot better by thinking through the problem, writing things down, designing things carefully, and coming up with a simple solution. Producing simple solutions to problems is hard work, but so it's really worth spending some time thinking actually hard about the problem, writing it down, discussing it with your colleagues. That can often lead you into simpler, better solutions, which are then end up being quicker to implement, easier to test, much more reliable. So that upfront investment, in my view, for difficult problems like the ones we face with blockchain implementations, is really worth it. So perhaps you meant it as a joke, but yeah, no, sitting around and talking is actually a remarkably effective way of producing quality code. Here's a nice question. Why have you decided to go with TCP and not UDP connections? So, okay, I think there's two answers to this one. One is what I said about stateful protocols. So, we actually really rely on that. At the application level, our protocols need to be stateful for the reasons that I discussed earlier. That you get the asymptotic analysis, you get the ability to associate, what did they do earlier with what they did later, and you can cut them off, and they have to, go back to step one. So there's various things where at the application level you really want a stateful protocol. Now that doesn't mean that you can't use UDP. You certainly can build, application level stateful protocols on top of UDP. But nevertheless, it's really a whole lot easier to do it on top of TCP. TCP really does buy you a great deal. It gives you, automatically that control flow, that retries, it adapts to the available bandwidth so that you don't try to overdrive the system and produce too much packet loss. It solves a whole raft of problems that you would otherwise have to re-implement yourself. Now, that's not to say that you should never ever do that. And TCP is not, the last word in networking protocols, but it's really a substantial undertaking to go and re-implement something on top of UDP when you do in fact need pretty much all of the features that TCP is giving you. So yes, you could do slightly better, but it would be a lot of development work, and it could still be worth it, but you'd probably still need TCP as a fallback, simply for getting through all of the firewalls and legacy equipment that's out there on the internet. It's actually very hard to deploy a genuinely new protocol, and to some extent even ones that are built on top of TCP. Built on top of UDP. So I'm not saying that we would never do something on top of UDP, but it's a substantial engineering effort, and it's not something that we would want to be doing before the Shelley release. We wanted to go for something that's reliable and that we know would work on the real internet. Here's a question. In this architecture, where do sidechains fit? So at the moment, they really don't. They're not in our current in our current implementation. Sidechains are, I think, still actually not a completely solved research problem. I mean, there have been a number of papers published, but I think we haven't quite got to the stage where everybody is totally happy with that. How would it fit in? The way when we have discussed the architecture of this with the researchers, the best one that we've come up with is a method that one of the methods that researchers proposed. They proposed a few different approaches, but the one that I think would work best is one that uses quite clever crypto to post evidence on one chain about what's happening on the other. And what's the big engineering advantage of doing that? I mean, it has more complicated cryptography, but the big engineering advantage is that you don't have to have the nodes that are operating one chain observing the other chain, right? You don't have to have the nodes themselves know about two different protocols, two different blockchains. You can keep them both focused on their own separate blockchains. And then you just have special agents that gather up information about one side and then they post it to the other side. But it means that you can verify each chain independently, and that's really a massive engineering advantage. So if we do go with that style, then the architecture that I've described will be perfectly adequate, because all we'll do is extend the ledger rules, and then we write these agents to do this cross-chain posting business. And you'll have to provide some incentives for people running those agents. I think I'll jump back to my slides for a moment, and then perhaps we'll come back to a few more questions later. Okay. So modularity. Yeah, I want to talk about the modularity of both the ledger rules and also of consensus, because this is another really big, important feature of the design. And in some sense, this is not sort of fundamental to blockchain systems. This is just like good design generally. You want modularity for all kinds of sound engineering and business reasons. So with the ledger rules in particular, the way that we've designed it is that there's a clear separation between the ledger and consensus, which means that the ledger rules can be specified in isolation on their own, and crucially, they can be written as if the world is completely static. There's no concurrency going on. There's just one single perfect view of history, right? They don't need to think about the fact that real blockchain systems are forking all over the place and things are constantly changing. You can have this very simple mathematical world of sequences of transactions, or sequences of blocks containing transactions. And that's a massive win. It's a win for simplifying the specification of your ledger rules, and it's a win for simplifying the implementation of your ledger rules. It also means it's much easier to test those ledger rules because concurrency makes everything difficult. So the lack of keeping concurrency out of the ledger rules is a big win. So in our design, all of the concurrency is handled by the consensus, and the ledger rules are completely pure in a purely functional sense. And Haskell makes it very easy to then implement and test. Well, comparatively easy to then implement and test those pure ledger rules. And it's a nice fit for a purely functional language to have a pure mathematical functional definition of those ledger rules. And what's the big practical win from that? It means that it becomes much easier to change the ledger rules. So it means that we can much more easily go from Byron to Shelley to Gauguin to Voltaire without having to, because each of them can be specified in this way, and we can swap one out and change them over. Or you could do private blockchain instances with different rules. Okay. Modularity of consensus. Again, modularity is a big theme. We have a really highly parameterized design of the consensus. It seems to be, if you go and look at it, it seems to be parameterized by absolutely everything. But what does that mean? It means that you get to choose how it's configured. You get to choose how you instantiate or how you plug in different choices. So it's parameterized over lots of different kinds of choices, and then we get to choose which choices we actually make in the actual system. And that means that you can change your mind more easily. It also means that you can plug in testing instances, and you can test the system much more easily. The consensus implementation is designed to support multiple instances of the Ouroboros family. And it has a relatively narrow interface with ledger rules, and that again makes it not too hard to write new ledger rules, because the sort of surface area of them is not too big. And if you go and listen to Edsko's talk later, where he will go into a lot more detail about the consensus implementation, he'll tell you again, generalization, solving a more general problem than you strictly had to, is really a big win This is slightly counterintuitive, solve the smallest problem you can, but it turns out that if you generalize and abstract over specific details, you can get to what are the crucial bits of information, what's the crucial design decisions, and sort of ignore the bits that are not so important. So generalization really, particularly in this area, leads to better design, and it makes it much easier to test. And because this thing is highly concurrent, testing is a challenge. And also, the modularity here gives us the ability to compose protocols, and Esker will talk about that particularly more in his talk. So I won't go into the details. I'll just advertise his talk for later. We make use of concurrency very heavily in the consensus implementation, and we keep it out of the ledger implementation entirely. And we make use of concurrency because fundamentally what the node is doing is concurrent. It's interacting with lots of other local and remote clients. And so we use concurrency, yes, to cope with those external interactions and also to maintain internal modularity. Like I said earlier, we have the separate threads for each client and separate threads for each protocol talking to each client, and we have multiple application level protocols. So we make very heavy use of Haskell's lightweight threads, because we've got several threads per client. That it's a little bit difficult in a heavyweight threading system like Java or C or Rust or C++. You can't use a design where you really use a large number of threads because those threads are just too expensive. Whereas Haskell's got these very lightweight threads, and so we can follow a design which has greater modularity and doesn't mush together so many things in one thread, but allow them to be split up into more logically decomposed, and not pay a huge performance penalty for that. And we also make very heavy use of a feature called software transactional memory, which is a big feature that came out of academia 10 plus years ago, and hasn't really caught on in other languages, but works extremely nicely in Haskell as a way of, in a very disciplined way, allowing threads to interact with each other. Because if you know anything about computer science, you know that concurrency is notoriously difficult, and STM really makes it substantially easier. It gives you a degree of modularity which you just don't get with traditional locks and even message passing. I think I'll jump on to the last part because this is kind of the big deal at the end. We were able to test this consensus implementation by making use of simulation, and we're able to do full-scale simulated testing of the consensus implementation with the full network, the full ledger, and consensus with multiple nodes all running in simulation, and we're able to generate thousands, tens of thousands of scenarios. And in particular, we're able to generate scenarios which you just wouldn't be able to produce in practice. If you're doing traditional QA, you just would not be able to produce these scenarios, which means you would not be able to find the failures that might occur in those scenarios. Whereas by doing these things in simulation, we can generate much bigger and much more complicated scenarios. And we don't do that by trying to think of lots of complicated scenarios. We do it by systematic random generation of complicated scenarios using a well-established technique called quick check with numerous techniques on top. So we're able to simulate extreme conditions, nodes joining dynamically, failures, network partitions, and check that the consensus properties are achieved, check that the nodes actually do achieve consensus when that's expected. Because we can also generate environments in which we know for sure that you could not achieve consensus, because we can push the limits to the most extreme cases where, we know it would actually be impossible to achieve consensus. But we can check that when we're within the predictable region of operation where we expect consensus, we can check that we do indeed achieve it. So, the big takeaway from that then is that we can uncover bugs, and we have uncovered bugs in our implementation which would never have been found by traditional means, and then we fix them. And then when all those tests pass, and it fails to find any more bugs, having found some really juicy ones, we then have a really high degree of confidence in the correctness of that code, and that's really our kind of secret weapon underneath. Running things in test nets is great, but they just don't find these kinds of deep bugs, whereas this technique does. So, conclusion, there's many kind of obvious design choices in here, but then there's also some interesting design choices which are really motivated by the problem we're trying to solve. And I've tried in this talk hopefully to focus on those slightly more interesting ones. So that's kind of my time. If you want to move on to the next talk, absolutely go for it. But I will hang around and answer more questions. I think I don't get cut off. But yeah, if you want to go to your next talk, go to the next talk. If you want to hang around and listen to me answer more questions, you're welcome to do so. Thank you very much for listening. So let's see, there were more questions. I answered the sidechains question. So Ken asks, designing a system like this from the ground up must include constant discussions of trade-offs with things like stateful protocols. What is involved in formally choosing one design over another? How much room do you leave yourself to potentially change your mind later? So it's a very nice question. To a large extent, the kind of early design is done by a relatively small number of experienced people simply talking to each other and then building prototypes. The talking is surprisingly useful for thinking through aspects of the design, and then building little, perhaps throwaway prototypes is good for checking that things do end up working the way you think they did, because it's quite easy sometimes to miss out certain details. So I think that combination of thinking, discussing, building prototypes, and iterating on that is really the sort of bread and butter of this kind of design process. Now, then the other aspect of your question is how much room do you leave to potentially change your mind later? What I like to say about that is that we follow a design methodology which is very simple. It's a bit grandiose to even call it design methodology, which is to solve the hardest problem first. Right? This may sound blindingly obvious, and frankly, I think it is, but you would be surprised to the extent that people do not do this. Right? People often make design decisions very early on because they're trendy or because it worked for them last time. Here's another way to think about it. You can design bottom up, or you can design top down, or you can design in a kind of agile manner, or you can design where you just build the minimal thing that works and then you keep expanding it with more features, or you can do as I said, solve the hardest problem first and build a prototype approach. Now, I would argue that the hardest problem first approach is really strictly superior when you have a problem that is really hard. Right? When you have a design space that is big and sparse, there's very few plausible designs that would really work. When you're dealing with a problem like that, which is the characteristic of hard problems, then I think this aspect of solving the hardest problem first really makes a difference, because it means that if you do it the other way around, perhaps it's a good way to think about it. You come along and later on you find some difficult problem and you go, oh no, I'm gonna have to change my mind, and this is gonna have to cause me to reset all those half a dozen of those design decisions I made earlier, and then you've wasted a whole lot of work. Whereas typically it's the case that if you solve those hardest problems first, you don't need to backtrack quite so much. It's not impossible. Sometimes you may make a few design decisions, having thought about it carefully, and then you get to a point where you discover, oh no, there's some fundamental problem and I do have to backtrack. But it tends to happen less often when you do that. So that kind of top-down design approach works, I think, quite well when you've got this kind of difficult problem space. Whereas, if you're building, a standard off-the-shelf REST database web business IT system, that's what I would characterize as a problem space that is quite dense with solutions. That there are many solutions that would work. You just have to decide which one you like. So that kind of problem lends itself quite well to agile methodologies, where you say, right, let's stick a pin there. We'll start with this minimal thing, and then we'll kind of do a local search as we add another feature and add another feature. And you're moving from, there's lots of possible solutions. The area is dense with solutions, and you're just moving between solutions. Whereas you can't really do that when your design solution space is so sparse. So thank you for that question. That's a bee in my bonnet. As I say, it sounds blindingly obvious, but you'd be surprised how infrequently people actually take that approach. Okay, next question. Jared asks, of all the database types available today, does SQL offer some advantages for use in question blockchain, Cardano, over all others, say NoSQL, document, graph, entity relationship model, etc.? I think the answer is that both SQL and a graph-style database would be, and probably even entity relationship modeling, would be perfectly reasonable solutions to this area. I think the nature of blockchain data lends itself quite well to a relational style. There's lots of things where you'd like to be able to query across, do sort of analytics, query across all time, the relationships between transactions and blocks and etc. I think the data simply seems to fit a relational model quite nicely, and then there's all kinds of nice ad hoc queries that you can do, and there's lots of applications that can make use of it. It's a very general purpose tool. If you go for SQL, standard database. So it's not to say that you could certainly write a DB sync application that reflected the data into a NoSQL document style database, one transaction per whatever. And that might be the appropriate thing to do for certain kinds of clients, certain kinds of client applications. But the good thing about the database style, traditional SQL database style, is it's just so flexible. There's so many things it can do. It maybe is not the highest performance, but it's very adaptable. And there's a very natural way of just sort of systematically reflecting the schema of the blockchain into a schema in the database. So you don't have to think too hard. There's a natural translation. But yeah, it's not exclusive. And I think the event sourcing style is actually strictly more expressive, although perhaps harder to use, than the database style. So it means that we have the opportunity to translate into more than one database if we need to. And as I say, we have a GraphQL API. At the moment, that GraphQL API is implemented on top of the relational database, but in principle, you could do it on top of a graph database. I think that would probably work perfectly well. Okay, any last questions? I think the people whose questions are remaining are no longer offline, but perhaps some people on the video might be interested. Okay, Kevin's last question that he set up for me just in case there were no more questions. This is a very complicated architecture. How do you expect to extend it to support smart contracts and other features? Doesn't everything have to be rebuilt repeatedly? Well, that's an easy one, Kevin, as you well know. So this goes back to the modularity question, the modularity issue that I was talking about earlier. We can, the ledger rules are very cleanly separated from the consensus algorithm, and we can rip them out and replace them, for private blockchain instances, for other custom applications, and for going from Byron to Shelley to Gauguin to to Voltaire. So if you are only changing the ledger rules and not changing other aspects of the system, it's really quite straightforward. You implement those new ledger rules. I mean, you have to, there's a fair amount of work in writing new ledger rules to make sure they're correct, etc. But then integrating them into the system then becomes relatively straightforward. So it is having invested all this time in making a modular architecture that will really start to pay off, over the next months as we integrate, not just Shelley, which is predominantly done now. It's running in all the test nets, but all those next sets of features as we start to integrate those into the pipeline and formalize them, and which is already in process. We have formal specs already for Gauguin, and then it's a matter of getting their executable specifications in and integrating it, and that should be a relatively quick process compared to a from the ground rewrite that we did for the whole of Cardano here. We're now only changing one of those bits within the architecture. Let me jump back to the that block diagram at the beginning. We're only changing one of these blocks, adding changing the Shelley ledger rules or adding yet another parallel set of ledger rules. And that's a much smaller piece of the architecture to change than what we would have had to do in the past based on the original Cardano implementation. Okay, I think I will stop there. Thanks everybody for taking the time to listen. I hope it was enlightening. Bye for now.